Welcome back. Welcome to part two of this bonus content. You have chosen wisely to come here. Let's enjoy some mathematics together. Okay, combinations. We talked about permutations, now we'll look at combinations. One selection from a specific set of objects is called a combination. The formula looks like this. If you still have the permutation formula in your mind, it's very similar. The addition is this extra r factorial here. This is set up the same way. N choose R. This means combination, N choose R. For combinations, order does not matter. If you remember, for permutations, order was very important. For combinations, the order is not important. Let's show you what that means. For example, let's say we have a deck of cards and there are 52 cards. You are playing a game where 5 cards are dealt to you. How many permutations are there for the cards in your hand? Well, when we set up the permutation, 52, choose 5, and you do 52 over those two subtracted, and you get this big number. That means there's 311,875,200 different hands of cards you could have. By combination, we're going to do the same calculation. 52, choose 5 cards out of 52. We do the calculation. Notice again, it's identical, except we have this extra r factorial, so 5 factorial here. The answer is this. Notice this answer is smaller than this one. And now let's talk about what order matters means. Since order does matter in permutations, those 5 cards, the number of hands you can have, 5 card hands, is this many, but amongst those are different hands of cards where you have the same 5 cards, you just have them, you receive them in a different order. So same 5 cards, different order. Whereas this one, it only counts all the unique hands. So it will not count the same 5 cards twice, even if the order of them in your hand is different. Let's take a look at that with some visuals. So let's say you were dealt a 2, 3, 4, 5, 6 of hearts. So again, for permutations, order matters. Look at here. Here's your 2, 3, 4, 5, 6. Here's the same 5 cards. They're just reordered. So let's say they're dealt to you in this order, and then they're dealt to you in this order. The end result, if you're playing cards, is you have the same hand of cards. But if you calculated that using permutations, it would count these as 2 different permutations. And that's why we had a bigger number here, because it counted these 2 as 2 separate hands, even though essentially they're the same thing. So in this situation, it said using permutations, these would be counted as 2 different hands because order matters. Whereas using combinations, order does not matter. So those 2 would be counted as the same hand. So using combinations, these would be counted as 1. And then therefore, order does not matter. So that's why our combination number is always going to be smaller, because it accounts for the fact that there's this problem here that you don't want to double count those in some situations. And going back to the formula, how that's achieved is when you throw that extra r factorial in there, you're dividing by r factorial. You're dividing by this number factorial. And by doing that number factorial, you're basically figuring out how many ways can you take 5 cards, the same 5 cards, and rearrange them in your hand. And that's what that 5 factorial gives you. It gives you the number of ways you can rearrange 5 cards in your hand. So when you divide by that number, you're dividing away all those extra things which are the same hand, essentially. All right, so just to recap, now that we're looking at permutations and combinations, permutations are all the ways to order selected items when order matters. Combinations are all the ways to order selected items when order does not matter. And let's again make this a little more clear through an example where we compare head to head once more. There are 3 students. Let's call them Neolids, Takrina, and Yorgi. 2 are selected with the first getting 100 and the second getting 25. So the first person gets $100, the second person gets 25. So here the order matters. For sure it matters because you want to be the first one selected. You want to get more money. So let's list all the permutations. Since order matters, we're going to list the permutations. So the permutations could be Neolids is first and then Takrina. That means he gets 100, she gets 25. Or Takrina first, Neolids. So now Takrina gets 100 and he gets, see, same people, but we're counting those as 2 possibilities because the order is important. Okay, we could have Neolids Yorgi or Yorgi Neolids. Again, the order matters because one person gets 100, one gets 25. Or finally, we could have Takrina Yorgi or Yorgi Takrina. We're counting all of these because order matters. Now, second situation. 2 are selected and given $25 each. So now they get the same amount of money. So it doesn't really matter what order you select them in. The end result is the same. So here, order doesn't matter. It's not important. So we're going to list all the combinations. So again, we can begin with all the same ones we had here with all the permutations, but now we can cancel away the ones that essentially show the same thing. So these ones mean the same thing. So we're going to cross it out because the end result is the same. Those two people get 25. It doesn't matter what order they came in. And same here, same here. So now when we look at combinations, we only have 3. There were 6 permutations of those 3 people, but 3 combinations when we select 2 from that group of 3. So that's an important distinction. And again, the way we cross that out is by the formula. The formula gets rid of that part for us. Let's take a look. So here's the formula. Here's another way to look at the formula, by the way. You can sometimes you'll see it written like this. So n choose r permutation looks like this. So we put our, and here's another, and so many ways to look at it. Here's 3 choose 2 as well. So 3 factorial over 3 minus 2 factorial, which is 3 times 2 times 1 over 1. And that multiplies to 6. So we can see there's our 6 permutations. Let's look at that one in this case for a combination. So the combination formula, again, you could see it written that way, or here's that way. Here's the formula. Here's that extra r that's been added. And we have 3 choose 2 using a combination this time. So 3 factorial. There's the 3 minus 2 is there. But we also have r factorial on the bottom. So there's that extra 2 factorial. So the top is the same. The bottom now has that extra 2 there. And that extra 2 is what changes the 6 into a 3, which basically divides out all the ways of rearranging those. So that's how combinations and permutations work. Now, more often than not, we will use combinations. They are more applicable to many situations. So going forward now, we'll probably be using combinations. Let's take a look. Here are some and type of problems. So in probability, we've talked about and. Let's look at it here. Shakespeare wrote 38 plays. 18 were comedies, 10 were tragedies, and 10 were histories. You want to read 3 comedies and 2 histories. So what are all the different ways you can choose 3 comedies and 2 histories? So we're looking at it this way. Let's take a look. This is a good problem. A good problem looking at how do you set these up. And yeah, let's take a look. So of the comedies, you have 18 to choose from, and you want to select 3. So 18 choose 3. And in this problem, it didn't say anything about you reading them in any order. Basically, the end result is you just want to read 3 of his comedies, 2 of his histories, and the order is not mentioned here. So the order doesn't matter. So we're using a combination. So 18 choose 3 works out like this. 18, and then 18 minus 3, and then there's a 3. By the way, in the combination formula, the 2 bottom numbers will always add up to the top number. Okay, so there's our comedies. Then we multiply by, because and means multiply. You know, like when we do probability, we say this happens and this happens, or then this happens. We always multiply those things. So you read comedies, then you read histories. So here's 10 histories to choose from. You're choosing 2. Here's our combination. If you work all those numbers out, you get this. By the way, you can do this on your calculator. Let me show you. Okay, hopefully you can see this calculator. I'm going to press on. And I've been doing some work there already. So basically you press math, then you can scroll over to PRB, which is probability, and there you can see there's a factorial symbol and there's permutations, combinations. So I'm going to choose combination. Whoops. Okay. So NCR, combination, enter. Now I'm going to arrow back to where it says answer because I want to enter in the first number, 18. 18. And oh, it got rid of the whole thing. That's great. Okay, let's try again. So I'm going to put 18 first. 18, math, probability, and choose R. So there's 18, choose 3, enter 816. So 816 would be result there. I would multiply by the result there, and I get this number. So there's so many possibilities for you to read Shakespeare's work. Okay, in the second problem, you are drawing cards from a 52 card deck. Find the number of combinations for each. So another and problem, you draw 4 kings and 1 other card. 1 other card. So here's your 4 kings. 4 kings out of a possible 4 kings. There's only 4 kings available. And then 1 other card. So 48 to choose from because you're not talking about kings anymore and you're choosing one of those. That works out to a very big number. Let's see what you get. Try with your calculator. Okay, after that, let's check some OR problems. Or remember, and usually means this, then this, which means multiply, or means this happens or this happens. So we're going to be adding probabilities or counts. So let's look at this. You will read at most 2 plays of any kind. 2 plays of any kind, which basically means you're going to read 2 or 1 or 0, because 2 of any kind means you're going to read, 2 plays of any kind, 2 or 1 or 0, right? Because that means 2 at most, so it can be less than that. So of 38, of his total 38 plays, you will choose 2. Or you will read only 1 of 38, so 38, choose 1. Or you will choose to read 0, because again, at most 2 means you're not going to surpass 2, but you can read either 2, 1, or 0. So 38 and you choose 0. So you add all those because or means add, and you can figure out that total there. Okay, also here's another or problem. You will draw 5 hearts or 5 diamonds. So let's say you are grabbing a 5-card hand. You want to see how many ways there is for you to get 5 hearts or to get 5 diamonds. So there are 13 hearts in a deck of cards. So you have 13 hearts to choose from, and we're trying to see the number of ways you can select 5 different hearts. It's a combination because the order doesn't matter. As long as it's one set of 5 hearts, that's the number of sets you're trying to count here. And then 5 diamonds is the same thing. All right, great. Let's move on from there. So we're going back to the problem that kind of introduced the first video of this, part 1 of this video series. So we have a 4-person committee, and it is choosing, a 4-person committee will be chosen from 9 men and 3 women. How many ways will result in a committee which has only 1 woman? So think about this 4-person committee in the end will be a committee that has only 1 woman. That means the other 3 positions have to be men. So see if you can calculate that number. And this diagram helps. We have our 9 men, which are going to fill 3 positions. And we have our 3 women, and they're going to fill 1 position. And again, so basically we're saying we have 3 positions available for 9 men. So we have, well, let's look at the women first. Sorry, we have 1 position available for 3 women. So 1 woman from a group of 3. So basically it's 3 choose 2. And that means 3 factorial over 2 factorial, 1 factorial. That works out to 3. Okay, and then we're choosing 3 men from a group of 9. And that means 9 choose 3. 9 factorial over 3 factorial, 6 factorial. And that works out to 84. One easy way to deal with these, if you don't want to use a calculator, is to think about this means 9 times 8 times 7 times 6 times 4, etc. This means 6 times 5 times, etc. So imagine this written out as 9, 8, 7, 6, and this written as 6, 5, 4, 3. You can cancel out all the 6, 5, 4 because the ones that follow 9 cancel out with all these. So all the 6, 5, 4, 3, all those cancel, and you're just left with 9 times 8 times 7 on top. 9 times 8 times 7. And on the bottom, 3 times 2 times 1. So 9 times 8 times 7, 3 times 2 times 1. You can cancel the 9 and the 3 to make it a 3, and you can simplify. Basically, you can simplify the fraction and make it very easily figure this out. Okay, now the last step is the committee is going to be made up of these number of women, this number of men. So we take that number and you multiply, because the committee has to be it's like back to the basic counting principles. You have this position can be filled by 3 different ways, and this here, that one line represents these 3 positions. So those 3 positions can be filled in 84 ways. So 3 times 84, it's like a tree diagram basically. Think of a tree diagram. You have 3 branches, the 3 women, and from each of those you have 9 men, but it's not 9 men, sorry. From each of those you have all the ways you can fill these 3 positions, and there are 84 ways you can fill that. So the end result is 252. A little bit tougher, as particularly considering we're not really studying this topic in detail. This is just a quick introduction, but if you figure that out, way to go. Okay, let's look at the next problem we have. And the next problem brings us right back to where we began this journey. It is the problem about 2 marbles being simultaneously drawn from a bag. And we had that issue about looking at this tree diagram and it seemed to imply that it wasn't simultaneous, that one was drawn and then one was drawn after because the probability went down. But let's take a look. How we can set this up. Okay, our probability we're looking for is the probability that we have at least one red. And we've already mentioned that the one red path is represented in three places here: red blue, blue red, or red red. So three of the four paths lead to at least one red. So it might be easier just to do a probability of one, which is a complementary event here, minus the probability of two blues, because the two blue path down here is the only one that leads to a not one red situation. So one minus that path, it might be easier to calculate. So let's begin with that. And the probability of getting two blues, rather than thinking of the tree diagram, let's ignore the tree diagram now, and let's think about drawing simultaneously. So if you're reaching into a bag and you want to get two blues, you are saying, well, how many blues are there? There's three blues. And we can say the three blues are three distinct ones, like blue number one, blue number two, blue number three. And if you want to get two blues out of a possible three, it's like you have a selection of three blues and you want to see how many ways are there for you to select two of those. And the number of ways you select them, the order does not matter, because if you select blue one and blue two, that's the same, like let's say in your hand you grabbed it and you're holding them, and laying in the palm of your hand on the left side is blue 1 and on the right side in your hand is blue 2. That's the same as if laying in the palm of your hand you had blue 2 on the left and blue 1 on the right. So the order of the two balls in your hand or marbles doesn't matter. It's the fact that you grab those two. So we're talking about a combination, not a permutation. We don't want to count that twice. We want to just count the number of unique things. So we're going to do three blues to choose from, and we're choosing two. So 3, choose 2. And we're setting up a probability here. So that's the number of ways to select blue, 2 blues, but we want to say that over the number of ways to select any two. Because, yeah, we're seeing basically how many ways are there to grab two blue marbles out of all the possibilities of two marbles you could grab. So that'll give you the probability of getting those two blue, right? So we have 3, choose 2 on top. And 3 choose 2 is 3 factorial over 2 factorial times 1 factorial. That, if you calculate quickly, gives you 6. Whereas on the bottom, we have 8 total marbles to choose from. And we're seeing how many ways are there to choose any two. Again, order is not important. So 8 choose 2 gives us this. That becomes 1 minus, this is 3. And this number is 28. Let's notice that that number matches what we have up here. If we did the blue path, it would be 3 over 28. So 1 minus 3 over 28 is 25 over 28. Because again, we're not looking for two blues, we're looking for at least one red. So 1 minus the 3 out of 28 ways that we can get a blue pair in our hand, we're left with 25 out of 28, which means 25 out of 28 ways to get at least one red in your hand. So that was a long answer to this question, but it's a very important question in probability, and it really is the next big step in probability from where we've been. Not part of this course, but certainly part of DP courses and also HL content and SL content. So very important. If you followed all the way through these two videos, congratulations. Thank you for joining me on this journey. I hope you can see how our combinations discussion led to this moment right here. All right, there's one more question for you to try though. It is this one. So if you understand combinations, here's a kind of easy but challenging at the same time problem. Try this one out. Okay, the answer to this one is it is a combination problem. It is 6 choose 3. The reason for that might not be completely obvious at first. So I would suggest if you want to get to the heart of why this is 6 choose 3, and that gives us 20, just put that into your browser and watch a quick 1.5-minute video, which very clearly shows why we chose this combination for this problem. Okay, maybe you got it though, so good for you if you did. Thanks for watching. See you next time.